I want to do an example today of just drawing a free body diagram. Just going through the steps to figure out the forces in a free body diagram and how to represent them, and then how to go on from that and use the free body diagram to write down Newton's second law in components. To do that, I've set up a ridiculously overcomplicated scenario of some crazy person who was on skis going up a hill being pulled by a kite up the slope. And I'm sure that the geometry of this is all ridiculous and it's not a very realistic scenario at all, but let's pretend that we have this set up, and I want to know what is the acceleration of this person symbolically. I've specified the mass m symbolically. We'll talk about the magnitudes of the various forces symbolically. I've put in some angles, definite angles, just because those are going to be useful to look at as we draw and interpret our free body diagram, to have something definite to talk about there. But for now, what I want to do is start by just getting a catalog of the forces on this skier. And when I do that, well, the way that I've learned to do a list of forces reliably is to draw a little dotted line around my system. I'm going to choose the skier to be my system. And so here's my dotted line that I've drawn around that system. And what I want to do is look at places where the outside environment contacts the system, where it breaks that dotted line, and I'm just going to list those forces. So, for example, right here, we have a point where the string from the kite, that would be a rope if it's pulling them hard, breaks the dotted line, and so that is a tension force from that rope, so there will be a tension force to think about. That's the only force at that contact point. Going on around, I've specified a wind force. There's a tailwind blowing at a specific angle, sort of downward angle, at relative to horizontal, at this skier's back. So there will be, I'll just call it a force of the wind. These are vectors, so I should specify those vectors. And that's the only contact force. I'm treating that as a single point, even though it's presumably blowing on the skier's back, all along the back. We've got that. We've got the contact point down with the ground, with this sloping ground. Anytime you have two surfaces pressed together, that counts as a normal force. There will be a normal force there. And, of course, anytime you have a normal force, you should ask, is there also a frictional force associated? Nothing says frictionless here, and in fact I've specified the coefficient of kinetic friction, so I will specify a friction force as well. That's all the contact points, so it should be all the contact forces in this problem. I also think about long-range forces. Nothing here has anything to do with electric or magnetic fields, thank goodness, but there is a gravitational force, Fg. Some textbooks will call this weight, W. Whatever you want to call it, there's a gravitational force on this skier as well. Once I've made this list of forces, once I've made my list, I can now draw a free body diagram based on those forces. And I'm just going to go through, for a free body diagram, I represent my system as a point, like so. And I'm going to go through my list and just draw these forces in. So the tension force, for example, is here, tension. And I'll go ahead and specify that relative to this direction, that's a 50-degree angle, because I'm copying that from over here. I want to copy angles in verbatim if I can, exactly as drawn. My wind force is down and to the right. It's a wind force that's something like this, force of the wind, and I've said that's 15 degrees below horizontal, so I guess I can put that in here. This is 15 degrees. And then, what else do we have? Normal force due to the ground. Well, the normal force is always, the term normal means perpendicular to a surface, so the normal force is going to be up this way. So there's my normal force. And if you want to get that angle right, the surface is tipped up by 10 degrees from horizontal here, so the normal force must be tipped over by 10 degrees from horizontal there. So this is 10 degrees. Got that. And my frictional force, if I am sliding up the hill, which is what I described, then maybe I should specify that. I have a velocity going up the hill. If I'm sliding up the hill, a kinetic friction force is going to resist that slipping. It's going to work against that, so it's going to be exactly down the hill. That means it's perpendicular to the normal force vector. It's exactly this way. My friction, kinetic friction in particular, I guess I could have called this kinetic friction here. My kinetic friction force, again, that's got to be that same 10-degree angle because it's tilted down, it's going down the hill. And finally, gravity. We know where gravity goes. Gravity points down. That's the definition of down, in fact, is where gravity points. So I've got this whole horrible mess of forces in my free body diagram. So that's my starting point for all this, is having my list of forces. I've translated them into the diagram with some angles there. The next thing I always do when I'm drawing a free body diagram is to make a note next to it about the acceleration direction. In this case, this crazy person is being dragged up the hill by their kite, and so their acceleration should be uphill. Unless the kite is really crazy strong, they're not being pulled off the ground, and I hope they're not delving into the ground. So they must be sliding along this snowy ground, and so I expect that to be tilted up at that same 10-degree angle. I can even label that here, 10-degree angle compared to horizontal that we had before. I've drawn that. Next, the next step I always do in setting up a free diagram, for setting up a free body diagram, is that I'll choose a coordinate system for that diagram. And boy, this is a mess. In a perfect world, you want your coordinates to line up with important forces and accelerations and things in the diagram to keep things simple. Now, in particular, my advice is, in almost every case, it's very helpful to choose coordinates that line up with any non-zero acceleration in your problem. By the same token, you want coordinates that will line up with any normal force in your problem. If you do that, then those are things that are often unknowns, or at least it makes your life much simpler if the acceleration is all in one direction, in one coordinate, not in the other. So in this case, it's pretty clear that my optimal coordinate system is going to be tilted to match the slope. So I will go ahead and draw that in. I'll have my x direction this way, and my y direction this way, plus x and plus y in those directions. And for reference then, I'm going to put that angle up on my free body diagram just by drawing a nice little dotted line through the center, tracing that along. Now we know the normal force and the frictional force are going to be exactly along those angles. And there are a lot of ways of thinking about this. I want to label some other angles here as well. Remember, I've tilted my coordinates from the traditional horizontal vertical by 10 degrees everywhere. So that means that this angle is 10 degrees, and this angle is 10 degrees. All those angles I know. All right, so I've done a pretty good job of setting this all up. The one other thing I know I'm going to want to do, since I'm going to have to write down things in components, in x and y components, I will want to understand these forces in components as well. So it's to my advantage to find right triangles in this diagram whose angles I know. And in particular, here's my plan. I'm going to choose, let's say, the gravitational force vector down here, and I'm going to say, how do I draw a right triangle that has this gravitational force vector as its hypotenuse, so not touching the right angle, and that has the labeled angle there, an angle I know, as an interior angle. Here's the trick. When I drew my coordinates in here, I've got a line parallel to y going through the tail of that gravitational force vector. So, and that line parallel to y includes the angle that I know. So I'm going to draw a line parallel to x through the tip of the vector, and those are automatically perpendicular. And now that I've done that, you'll see that this is going to be an x component of force, so this is going to be the x component of gravitational force, and this side will be the y component of the gravitational force. Just drawing it in like that. And I can keep doing that. The friction force and the normal force are directly along these axes, so I don't need to do that. What about the force of the wind here? Well, I can see a total angle of 25 degrees compared to the x-axis here. And so, since the x-axis, where I know that angle, goes through the tail, I can draw a line parallel to the y-axis through the tip. Get this right. Right angle here. And suddenly, that's a right triangle with the wind force as my hypotenuse, and with the known 25-degree angle, over there. So this will be the y component of my wind force, and up here, this will be the x component of my wind force along that side. Sorry, it's getting a little squeezed in there, but that's what happens when you have way too many forces in a single free body diagram like this. And then finally, for my normal force up here, for my tension force, well, I could draw a right triangle here, but the angle I know of, it's a 60-degree angle over here, and so I just need to draw, this is a y-axis going through the tail, so I'll draw something parallel to the x-axis going through the tip. It'll go right on top of my numbers, but that's okay, and that means that this side is going to be my t sub x, and this side will be my t sub y. Those will be my tension components. I've done that. That gives me an idea of how to set up this free body diagram. I've done everything I can with the free body diagram now. I've figured out all these things. Now it's my job to write down Newton's second law in components. Newton's second law, remember, says that F net as a vector is equal to the mass times the acceleration. And F net as a vector is just the sum of the tension vector plus the wind vector, plus the normal force vector, plus the frictional force, the kinetic friction vector, plus the gravitational force vector. That is Newton's second law as a vector equation. So my next job is going to be to write this in components over here. And abracadabra, over here. Sorry for the jump, I had to stop to meet with a student for a minute. We're going to write this in components, and so writing that net force in components, I'm going to write this in separate equations. You could do it as unit vectors, I hats and j hats, or x hats and y hats, but I'm going to write it in separate components. And so I'll start by writing the x component of the net force. And for this first line, I'm just going to be completely straightforward, plowing ahead. I'm just going to write out x components for each one of these. So each force, tx plus the x component of the wind force plus the x component of the normal force plus the x component of the kinetic friction force plus the x component of the gravitational force. I've just written that out, straight out, no complications or anything. And I'll do the same thing for y components. And again, this is a completely mindless step. The y component of the net force is equal to ty plus fy for the wind force plus fy for the normal force plus fy for the frictional force of kinetic friction plus fy for the gravitational force. There was no creativity in that. I just took the list of forces, I took my second law equation as a vector, split it up into x and y parts. Cool. I've done that. Now is where the free body diagram really pays off. Because in my next step, this is where I go from these, and the way I like to do this is I'm going to take my tx, and now I'm going to write it in terms of a magnitude and a direction. A direction and a magnitude. Direction for a component is just plus or minus, or 0. And then the magnitude is just the magnitude. So in our case, for example, I'm going to start out with tx, the x component of tension. And I look up here, so fx net equals, what is my x component of tension? Well, it's in the plus x direction, so I'll put a plus here. Magnitude is just capital T, that's my convention for the magnitude of a vector, is just that thing without the vector sign or any component. And then I'm looking for tx, right? I'm looking for this component. That I know the angle down here from the y-axis down to the tension vector is 10 plus 50, 60 degrees. So this will be opposite the 60-degree angle. Opposite is sine. So this is t times the sine of 60 degrees. Fx for the wind force. Wind force here we've talked about. So that will be plus, it's in the plus x direction. So plus F wind times, let's see, the total angle I have listed here is 25 degrees, and the x component is adjacent to that. In this picture, you can see Fx wind is adjacent to my 25 degrees. So ca toa cosine of 25 degrees. Then normal force plus 0. There's no x component of my normal force. Next up, kinetic friction is in the minus x direction purely, and so that'll be minus my kinetic friction force magnitude. It's in the minus direction. And gravity, looks like my gravitational force is a little bit in the minus x direction as defined there. So it's going to be minus, and force of gravity, I know the magnitude is mg times, let's see, I know the 10-degree angle, so I'm opposite that 10-degree angle, so it's going to be sine of 10 degrees. That's that. Oh, and I've just realized, I said I was writing down Newton's second law. I left out a piece, right? My Newton's second law equation, this is Fx net, equals this, and it equals the mass times Ax. And this will equal the mass times Ay. Got to keep those in if I'm writing all of Newton's second law down. And so this thing will equal my acceleration. My presumed acceleration is in the plus x direction, and it is along my x-axis. So this is going to be plus mass times the magnitude of acceleration, plus ma. That's my acceleration, and I've got that set up. And then I can do the same thing for y. I can go through the same process. Ty down here is going to equal, well, my y component here, that's in the plus y direction, it looks like. So it'll be plus the magnitude of the tension times y is adjacent to my 60-degree angle. So cosine is adjacent, so cosine of 60 degrees. It's different than that. That's a good sign. Wind, same thing here. Y is opposite my 25, and it's negative. So minus F wind times the sine of 25 degrees. Normal force is all plus y, so plus Fn. No cosines or sines necessary. Then plus 0, because the frictional force has no y contribution in my tilted coordinates. And then my gravitational force is negative, so minus, again the magnitude is mg, and cosine is adjacent to that angle, cosine of 10 degrees equals, and my acceleration is 0 in the y direction, so that equals 0. So right now, what I have is a pair of equations, Newton's second law equations, for the x and y components taken directly from my free body diagram. I was just able to read them off directly based on the angles I've already labeled in here and the directions I've already labeled. And when I do this, I guess the goal here was to find a symbolic expression for the acceleration. And if I look at it, my acceleration only shows up in the x component. And so all I need to do to answer that is to divide both sides by the mass m, and I'll be set. I guess I may as well write it down, but it's not going to be very informative. Maybe I won't bother. Well, I said I'd do it, so I'll do it. My acceleration is equal to, what do I have? T over m sine of 60 degrees plus the wind force over m times the cosine of 25 degrees minus the kinetic friction force over m minus, and then divided by m, this will be g sine of 10 degrees. That is my acceleration magnitude, and it's pointing, that's the magnitude, and the direction is uphill. And that's what I come up with. So that's how I do this, that's how I'd use a free body diagram to get my Newton's second law equations and work out solve for some unknown. Of course, if I needed to know something, oh, I guess I did say there was a friction component, didn't I? Oops, so there's a piece I left out. To find my kinetic friction, I still need to plug in for Fk. Oh, this will be ugly. If I want to go ahead and do that, maybe it's not worth our time to go through and do that. To find the kinetic friction force, I would need to then say, oh, I know that kinetic friction is equal to mu k times the magnitude of the normal force. And I've got that in this equation down below. I've got the magnitude of the normal force. I can just solve down there for the magnitude of the normal force. This seems like kind of a pain to me to do. I hope you get the idea already. But if I do it, this would be mu k times solving I'd have my mg cosine 10 degrees minus t cosine 60 degrees minus or plus wind force times the sine of 25 degrees. I'd have that. I can plug it in up here in my acceleration equation, and suddenly I have some kind of answer. I have some kind of result that would give me a number for the acceleration. It's symbolic. It's all going to be ugly. I think it's really not worth our time to plug that in. But you get the idea of how I can solve a problem like this. I take the story, I identify the forces, make a list if I want to, use the list to draw a free body diagram, labeling all the angles, figuring out how I'm going to draw right triangles to identify x and y components for whatever tilted coordinates I chose when I drew my free body diagram. And then I'm just going to write down Newton's second law components and use that to solve for whatever unknowns I'm supposed to solve for. This is a particularly ugly example just because I want to show how you deal with an ugly example, but the principles will apply to just about any problem you might do.